Welcome to Axon Hub, where we turn wireless communication theory into real-world insight. Today, we will explore bit error rate, which is BER analysis for BPSK in Rayleigh fading channel. We will cover theory, derive the equation, and walk through the practical implementation plus simulate it into the either Octave or MATLAB. Rayleigh fading is a key concept in wireless communication. It models scenario where there is no direct line of sight, which is LOS, between transmitter and receiver. Instead, signal arrive via reflections, diffractions and scattering, where creating multiple delayed copies called multipath components. These multipath components interfere with each other, causing rapid variations in signal amplitude and phase changes, commonly known as a fading. This fading is significantly affect communication system when signal amplitude drops severely, which called as a deep fade. Even a strong transmission can result in a bit error. This makes Rayleigh fading channel for more unpredictable than basic additive white Gaussian noise channel. When it deals with the channel performance, signal to noise ratio, which is SNR, becomes a critical metric. Higher SNR, better quality. Lower SNR will be especially under the Rayleigh fading. Usually, binary phase shift gain, which is BPSK, is widely used in digital modulation scheme. It encodes bits in two phases. Bit 0, which has a phase 0, which will transmit the data as +1, whereas in bit 1, which always gives the phase as a 180 degree, transmitted as -1. So BPSK is power efficient and noise tolerance method, but in fading channel, even this robust modulation face distortions. When it comes to the mathematical model, let's define signal model under Rayleigh fading, which always signifies with the equation as y equals to h into s plus n. So here the s is transmitted BPSK symbol either in the form of +1 or -1. H is nothing but complex Rayleigh fading coefficient and N is nothing but noise. At receiver end, we will perform equation by dividing this by H. So which gives S vector equals to Y by H, which is nearly equals to give you the S plus ratio of N upon H. So this removes channel effect, but here there is a catch. The catch is if vector of H is small, it will be considered as deep fade, and N by H becomes a large, where the noise overwhelms the signal, which leads to a strong bit decision. In terms of that, whenever the kind of equation will come out as a bit error equation, bit error rate, BER, every time the Rayleigh versus additive white Gaussian noise will be considered as in AWGN, where no fading are there, this particular bit error rate comparison expression will becomes PB equals to Q to the under root of 2 EB by NO, and Rayleigh fading equation becomes PB equals to half of the rate of 1 minus square root of gamma divided by 1 plus gamma, where you can consider gamma as a ratio of EB by NO. So Rayleigh fading causes a significant performance drop in BER even at the same SNR as compared to AWGN. So in simple words, BPSK, the benefit of taking this BPSK is it is simple, reliable and power efficient, performs well in low SNR environment, ideal for IoT devices, wireless LAN and low power modems. While it's not the most spectacularly efficient, it provides predictable performance and it is easy to simulate and implement. Now in real world impact and mitigation techniques, in real system like 4G or 5G or IoT, Wi-Fi and satellite links, relay fading is everywhere. To combat it every time, engineers use diverse techniques, maybe MIMO, forward error correction, FEC, OFDM modulation, which is usually get benefited in terms of 4G and 5G. Now, let's simulate BAR for BPSK modulation in relay fading. So this simulation helps us to understand how wireless channel behave in real world environment, especially when there is no line of sight. A quick recap: when we transmit signal wirelessly, we don't know actually allow what kind of line of path, straight path or any other path the signal is taking. So usually signal reflects off building, scatter from trees or distract from in and around obstacles. So this causes relay fading. So in BPSK modulation, bits are transmitted as +1, -1 in relay fading, where the signal amplitude and phase are randomly altered. If the signal amplitude fades too much, even the strong bits can be received incorrectly. So rising these bits can cause bit error. So simultaneously we have already discussed the scenarios of additive Gaussian white noise as well as the relay. So in the both of the scenario, we'll be checking it out, the comparing both of the relay fading all together in the simulation here. Now in the purpose of the modulation, we are considering the scenarios of defining the range of the simulating noise, where the EB by N0, number of bits, error bits, that is being considered as a minus that are being considered here as a 0 to 60 dB, with which we will loop through to analyze the performance under the different noise scenarios. So for BAR calculation, we are considering here as the simulated error number of bits, where the number of bits by BAR calculation can be, sim BAR can be able to evaluate it. For the theoretical BAR by additive void Gaussian noise, from which error function can be evaluated, and by means of that we will be able to compare it here. So in the BAR calculation, the channel noise and the noise addition cancellation can be here utilized by means of the equation y equals to product of H and S, which is again later on the part is being equalized. And the noise equation for the white noise as well as the relay channel is being put forth as a N and H as per the equation. Once we simulate this, we will be able to compare three results of BAR, where additive void Gaussian noise, relay and the theoretical BAR values can be evaluated. Now to simulate this, after the simulation, you will able to see the BAR for the BPSK modulation relay channel graph, where, as I have already told you, that we will be comparing three of the values all together, where AWGN, relay theory as well as the simulated relay BAR values will be able to compare. Now as per this graph, this can able to show that whatever the pink color is there, that is the relay simulation, and the AWGN, which is in the sea blue color, which is reflected as a AWGN as the BAR. So this shows the best case performance of your BAR, where BAR decreases exponentially with increase in bit error rate, right? So this is the baseline for performance for in a ideal and no fading scenario. While as in for the Rayleigh theory as well as the simulated value, the model will simulate multi-path fading. So without the direct line of sight, the BAR here is much more worse than AWGN, where for the same SNR. So decrease in BAR is slower, especially at a low medium rate of SNR levels, right? Where for the Rayleigh simulation, the kind of blue color highlighted graph will represent the practical implementation as we have done it for the 10 to the power 6 bits. For that purpose, we are able to perform it for the BER calculation. So this follows the theoretical Rayleigh curve very closely. So validating the accuracy between them, the accuracy of simulation will be same as that of your theory part. So slight fluctuation may able to see it here, but due to the randomness in the channel, the fading and noise which is in the form of equal in the simulation here. So from this, the kind of key takeaways is your AWGN here, the performing is better than the Rayleigh channel. So Rayleigh is able to perform it in the moderate way. So only the multipath causes the signal attenuation and phase shift that leads to some kind of more errors into it.